First of all, I would like to thank you and Martine for the invitation to talk in this autumn school. It's a great pleasure for me. Actually, it will be my first Zoom lecture, so I hope everything will go on smoothly. And just to make a link with the introduction of Volker, I would like to tell to all the audience to make some advertisement for the University of Trier, because I've been there several times. I've been collaborating with Martin and his group, and I think it's a very nice place, a very active group, dynamic, and I encourage all of you to establish contact with them, to visit them, or to send your best student there. So this is the first thing I wanted to say. Now, I've been asked to talk about linear bilevel optimization, but I decided to open, to widen a little bit the topic of my talk. Given that I'm the first speaker of this school, whose topic is bilevel optimization, I thought that there might be, of course, there are people who are very well aware about what this bilevel optimization is, but this is a school, so I think there are many people, PhD student or young researcher, who are not aware about bilevel optimization or who know little about it. So I would like to start first by introducing you to bilevel optimization and to give you some examples to explain you what are the tricky things, the issues when you consider bilevel optimization problem and so on, a little bit of history as well. And then I will switch to linear bilevel optimization. So somebody told me that there is a typo in this first slide because it's written Modelo de Stackelberg, but it's not. It's just because I have some attractiveness, let's say, for Spain, and I found a nice picture that I thought was good to represent, to illustrate bilevel optimization, and this is written in Spanish. So what is this? This you see here, Modelo de Stackelberg, leader follower. The main idea behind this, I will say much more about this in a few slides, but the fact that bilevel optimization is characterized by this leader follower aspect. You see here, you have one red guy. This is the leader. There might be several leaders here. This is an example with one leader and several follower. And I will explain in a second what this means. Oops, I try. Okay. So what all this means. So to start with, as I said, I will explain you what is a bilevel optimization problem and a little bit of history. I think it's always nice to put this in context. So here is a very general formulation for a bilevel optimization problem. So what is it? And I suppose that you are all aware, you all know what is an optimization problem, a single level optimization problem. Single level optimization problem is what you look at the first two lines here. You see, you optimize a function. Here, you may assume that X and Y are two vectors of variables, and those X, Y should belong to some feasible set. So this is a clear, simple, well, not simple, but very general single optimization problem. But here we consider a bilevel optimization problem, which means that you see here I made the distinction. I have two groups of variables, X and Y, and I assume that Y, this vector, is constrained in a particular way, in the sense that Y is the optimal solution of this, what I call the second level optimization problem. You see, Y, so here in this part, X is given. For a given X, here I optimize on Y under some constraints. I have an objective function that I want to maximize. So this is the specificity of bilevel optimization. You have a nesting of two problems. You see, you have the first level, And in the first level, what we call the leader, or the first level, takes some decision. So decides upon the value of the vector x. And then once this is done, the second level, or the follower, reacts with respect to this x decision by solving an independent optimization problem. Well, it depends on the decision X, but the second level decides upon Y, and then the game is over. Let's say it's a game indeed, but I will say this in a second. So this is the specificity of bilevel optimization. You see that you have constraints saying that a subset of variable is the optimal solution of a second optimization problem. Okay. Now, from an historical point of view, one could say that this kind of concept traces back to the beginning of the 20th century. There was a mathematician and economist, Heinrich von Stackelberg. In fact, he was born in Russia, and then he was educated in Germany. He studied mathematics and economics, and he was professor in Germany until a couple of years, I think, before he died. And then he moved to Spain, to Madrid, to the University Complutense, and died in 1946. Now, this person, Heinrich von Stackelberg, his contribution is that he considered a game in economy, which is precisely a bilevel optimization problem. So he considered two competing firms, two competing companies, but with somehow an asymmetry in the story, in the sense that there is a company, a firm that is the leader, and then the other one that is the leader. So one somehow dominates the other, takes decision first, and then the other reacts. And he considered a simple game in which each firm, so the leader, then the follower, decide upon the quantity of the product they will offer on the market. And once, so the leader decides upon his quantity, and then the follower decides upon also its quantity, and the price of this product on the market is a function of the total demand offered by both firms. But the second level, the follower, when it takes his decision, is totally aware of the decision of the leader. So the quantity, let's say Q2 of the second level, is decided taking into consideration the quantity Q1 that has been offered by the leader. And then the leader takes this into consideration, is aware of the situation. So is the problem, the whole problem consists in deciding what should be the quantity Q1 optimal, so that would maximize the profit of the leader, knowing that the follower will react optimally, and so on. So this is what Stackelberg proposed, considered in the beginning of the 20th century. And in fact, if you now consider the domain of operations research, it's much later that this kind of idea emerged. And it's in a paper published in Operations Research in 1973 by Bracken and McGill, in which the first bilevel model was proposed. And also in this paper, some structural properties of bilevel optimization were considered, as well as a military application. Okay, so this is enough for history. Now, what I would like to do now is to give you some applications, to present you some problems that are bilevel optimization problems. so I will give you 2 or 3 different problems just to show you how we model this, to give you a bit of a flavor. And then I will, after that, I will talk about modeling issues, properties, so general ideas about bilevel optimization. So in fact, this bilevel concept is very interesting in the sense that it presents many applications in different domains. I explain you the model that was proposed by Stackelberg. So this is, you can see this in what is usually called economic game theory. But there are also many other applications in production planning. This is the first example I will show you. Then in revenue management is the domain in which you want to determine somehow the price. You want to maximize your revenue by selling a product that is, I would say, perishable. For instance, a flight ticket. This is a perishable good because a flight ticket is valid for the day for which you buy it. After that, it's obsolete. You see? So revenue management is a place in which this kind of aspect is considered, and the issue is to maximize your revenue or your profit by selling goods, let's say. But also there are many applications in security, and I will talk about that also a little bit later. Okay, so some example, and the first one is a production planning that I've been considered with colleagues from Mexico and from Sevilla. So this is a problem that comes from an application in the petrochemical industry in Mexico. So there were 2 vertically integrated industry, in the sense that you have a first industry in which you have a company that is state-owned. This is a monopoly, and this monopoly produce the supplies for the secondary industry. Let's say this is the oil, for instance. And then you have different type of oils, and these are refined, can be refined further. So, and this is the secondary industry. And here I assume that there is one, for simplicity, one company in this secondary industry that is a private firm, and it competes with the state-owned firm, and they produce the same commodity. All of them have a limited capacity, and the state-owned is the leader, wants to determine which quantity it is. You see here in this, you have the state firm. This the state firm is deciding which quantity of each oil or each product it will refine by itself, and which quantity it will sell to the private company which owns several plants. And this company, this private company, is going to process the different products in the different plants in order to maximize its revenue. And the goal of the state-owned firm, in fact, consists in meeting the demand from the market in the best possible way. So let me show you the model of this problem and explain you how it works. Okay, so here you see you have 2 levels. You have here the first level in which the leader decides upon the quantity it is going to process by itself. So Xi is the quantity that the leader is going to process of product I. And this is also limited. It has a certain quantity available, or is not able to process more than this quantity, let's say. And then this leader, this state-owned firm, decides which quantity also it is going to propose to the second level, to the private company, to be processed with its different plants. So these are the two main decision, I would say, that the leader is going to take. Now, there are some constraints. First, these constraints, in fact, are devised to determine the excess, the surplus, or the loss with respect to the demand. So you see, Yij is the quantity that plant I is going to produce of product I. So this is the total production of product I of the second level. This is the production of product I of the first level. And it should be as close as possible from Di, which is the demand of the market. So the leader is decides how to dispatch the quantity to keep it for itself and to have processed by the private company in order to meet the demand in the best possible way. And here we have a constraint saying that the profit that the leader obtains from processing this product I must be at least a certain value T. So there is a lower bound on the profit. So he wants to meet the demand as well as possible, given that it's getting a certain profit. And then you have here the second level, which determines in which the followers or the private company decide how it's going to refine the different products. So this company owns J different plants. And here you have two groups of constraints. You have some capacity constraints. So the plant I cannot produce, is using some resources of some of the plant, which means that this is the total quantity that this plant may produce. And here, this is the constraints explaining how the raw material I can be used to be processed by the different plants. And also there is a limit, of course, given by Zi. So you see, this is a second, this is a bi-level optimization formulation for this problem. And just one characteristic I would like to stress is that this is what we call a linear bi-level optimization problem, in the sense that all constraints and objective function are linear in the variables. Okay, so this is the first example. Now, how we, I'm not going to detail how we solve the problem and so on. I would like just here to show you an example of a bi-level optimization problem. Now, as I told you as well, there are many applications in revenue management. And here I just show you a different picture, different illustration. And you see this first illustration about the toll booth. This is, in fact, I think the first problem I've been working on with a colleague from Montreal, mainly Gilles Savard and Patrice Marcotte, on toll optimization. So this is a bi-level optimization in which you want to imagine that you own a highway, and you want to determine what should be the price of each segment of the highway for the driver when they use it, in order to maximize your revenue. And then you have potential users of this highway. This is the second level. And here the first thing is that, in fact, you have several followers, because each potential user can be seen as a follower, independent follower. And each follower decides, wants to travel from one origin to a destination. We call it usually a commodity. And each user is going to travel on a path that is optimal. That means that is going to minimize the total cost. What is the cost of a path? Well, you have the toll, if you use some toll arcs, plus some value that corresponds to the travel time, or they may correspond also to the gas consumption and so on. So here you have a bi-level optimization problem in which the leader, the owner of the highway, decides on the toll you put on each arc of the highway, and then each follower decides which path is going to use to travel from his origin to his destination. Okay? So this is the first example, but there are many other of this flavor. Here I show you a picture of, this is a file of truck. In fact, there are different way to determine tolls. And this is now the case in Belgium, and I think it's the case in Germany, in the sense that there is a toll that trucks have to pay, but it's not, you don't have toll booth and it's not by segments. It depends simply on the kilometer, the number of kilometers you travel. Okay, so it's a different type of pricing problem, but the idea is the same. Now you need to determine, let's say, per type of trucks, what should be the price per kilometer. This is the decision in the first level, and in the second level, you have the different trucks that would, or different companies, trucking companies that decide which path they should use. And here the idea is that, of course, again, if you use if you use the roads on which you have to pay the toll, it's because it's faster, but it's more expensive, but you gain from the time. It's a trade-off between time and price. These kind of problems are also very frequent in the other industry, related transportation industry mainly. You see here a train and an airplane. Well, in fact, this is, you know that very well, that price for flight ticket or train ticket are changing all the time on the web. And so when you log on the website, you want to buy a flight ticket, the price may change soon. And this is because company optimize their price with respect to the competitors, and also, of course, they take into consideration the behavior or the utility function of the potential buyers. So you have a leader, which is the company, the train or the airline company that sets the price. And you may have a price for different type of tickets. You have different destination, but you have also tickets that you cannot, that are not refundable, or for which you can change the dates, and so on and so forth. So you have a different type of products for which you need to determine the price. And your goal is to maximize your revenue, given that potential buyers choose the product that fits them best, in the sense that it maximizes their own utility. So depending whether you are a student or a business person, your utility is different, and your choice might be different. Okay, so the goal here is to determine in the first level the price. You have a very similar type of problem for hotel. If you go to booking.com, which is a website for booking hotels. You know that the prices are changing all the time as well. It's the same type of problem. Um, but you have similar things also for express deliver mail, for instance, or for company selling internet and mobile packages, because usually they offer you bundle. They offer you, okay, you have the internet plus mobile for that many minutes, plus blah, 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 and so on. And you have different packages. And so the goal is to determine what should be the price of those different packages, given that you have different type of customers again, and you want to maximize the profit. Also, similar thing for cruise. In fact, about 20 years ago, with colleagues from Montreal and also from Lille, we started a startup, a spin-off company who is developing now an application for railway pricing. And at that time, we were also contacted by a cruise company who wanted to also determine what should be the optimal price for cruise, because you have different type of products as well. So you see, these are many different type of applications in which it's centered around pricing, but it is by level, definitely. And here is a very basic, maybe the most simplest pricing problem. It's not easy, but I mean, it's the purest, the most academic one, just to show you an example of pricing problem, how to model it. So the idea is the following. Here you have one seller who is the first level, the leader. And this leader is proposing several products on the market. And he or she wants to determine the price it will offer, the price of those products on the market. Now, his goal, of course, is to maximize his revenue. But of course, there is a second level, and here you have several second levels. So you have here different group of customers having different utility function. Usually they are called segments. And for each segment, we have a value Rij. So for segment J and product I, Rij represent what is called the reservation price of consumer in this group for the product I. And the reservation price, you can see it as the maximum price that the consumer group CJ is ready to pay for product I. Okay. And now the group CJ is going to buy the product I for which the difference between the reservation price its reservation price Rij, sorry, minus the price of product I, PI, is as large as possible. So you see, if you have a very large reservation price and a low price, that means that this is a good business for the consumer, he likes it. And if the price of the product is higher than the reservation price, this customer considers that this is not an interesting product for him or her. Okay. Just one remark. I hope you won't mind, but I'm going to say he all the time when I talk about the leader or the follower. He or she is complicated. I prefer to stick to he, and this is it. But it can be a male or female, doesn't matter. Okay. Now, what is the formulation of this problem? So you see, maybe one thing I forgot to say that is for me clear, but I forgot. I need to specify it, is that each consumer group wants to buy 1 unit of a product, exactly, at most. Okay, so this is a single item problem. Of course, you can generalize it, but here, as I say, I give you here a problem that is, let's say, maybe the simplest, the cleanest academic one. So you see here, I will use variable xij to represent the decision of consumer J. So xij is equal to 1 is consumer J buys product I and 0 otherwise. Okay, so this is here, we have the objective of the first level of the leader, which consists of in maximizing its total revenue. So we sum over all product, and then for each product, we have the price times xij for each consumer group J. This gives the total revenue that the leader gets from product I. And so we sum here over all product I, and we get the total revenue of the leader. Now, of course, we have constraints, and this is a bi-level optimization problem. So in fact, here, what we have as constraints only is we say that, in fact, the variable xij, the decision of the buyers, are the optimal solution of a second optimization problem, which is here. So Mr. J, the consumer J, is going to decide to buy a product, at most one. And if he buys one product, it will be the one for which the difference between the reservation price and the price of the product is as large as possible. So you see here, for instance, given that here we have smaller than or equal to 1, if imagine that if the price of all the products are bigger than the corresponding reservation price, then this customer is not going to buy anything. But if at least one product has a price smaller than his reservation price, he's going to buy the product for which this difference is as large as possible. Okay? And the leader wants to maximize its profit. Now, this is a bi-level optimization problem that has been proposed, considered by Dobson and Kalish, in 1988. This problem is strongly anti-hard already. It looks very simple, but it's not an easy problem. And one specificity, as it is mainly for pricing problems, is that here we do not have a linear bi-level optimization problem. You see, the first level optimize on the prices PI, on the prices PI, so PI are variables and xij are the second level variables. So we have a problem here in which both objectives of the leader and the follower are non-linear. In fact, they are bilinear because we have those products of PI and xij. Okay? So it's a different type of product price of bi-level optimization problem, I would say. Nevertheless, it shares some commonality with the linear bi-level optimization, like the one I showed you for this production planning. It's the following. Once the first level variable are decided, so here the PI, the second level problem is a linear problem, you see? And so this is something that is very important and that we will exploit later on. Okay, so this is one important aspect as well. Okay, a third type of application also I would like to present concern control, protection, security, and so on. Here you see different illustration. It's related to game theory, or let's say to bi-matrix game theory, as I will explain in a moment. So let me tell you the story around each of these thing, and then I will explain you what is the general idea. So the first illustration here, you see a lot of trucks on the highway. And the fact is that in many countries, maybe in all, I don't know, there are regulations regarding the trucks, in the sense that the driver cannot travel more than a certain number of hours per day, a certain number of kilometers maybe. The truck should have should be, of course, in good condition, should not be overloaded, etc., etc. Or there are also some trucks carrying dangerous products. So all these things imply that it's necessary to make controls. There are some control stations to verify that the trucks are in good condition and everything is okay. And so the idea is that if you put a control boot somewhere, always at the same place, the guy who does not comply with the regulation knows it after a while and is going to make a detour. So the control station is not very efficient if it stays always at the same place. So we should find another way. Here you have the same thing. This is an endangered species, let's say, in a natural reserve. Maybe you remember some lion that was shot by an American dentist some years ago in Africa somewhere. It was a scandal. Well, there are many elephants also in natural reserve that are shot by, what is the name of this guy, contrebandier? Well, anyway, poachers. And so there's a need to protect these animals. And so there are guards, but again, if you put the guards always at the same place, well, the poachers detect that and they avoid this place for hunting and so on. So again, you need to find a better way to protect the reserve. Here on the left, you see a metro or public transportation ticket from Brussels. And it's to illustrate that there are many cities in which it is, there is no control at the interest of the public transportation, but there may be some control at some other time, from time to time, because otherwise people don't pay the tickets. You see how do you do this? Again, if you have patrol verifying the ticket every day on the same line at the same time, the people who don't pay the ticket, they know that, and they take another line or they travel at another time while they choose a way to avoid the control. This is another, the one in the middle below corresponds, you remember, to September 11. It's the idea here is that also if you want to protect some targets that can be attacked by terrorism, by terrorist bad guys, and so on, which is more and more frequent nowadays. Again, if you put the protect groups, the group protecting those targets, you always choose the same. Assume you don't have enough resources for protecting all the potential targets. Of course, the terrorist, the bad guy, will decide to attack the things that are not protected, so you need to find another solution. And finally, this is an illustration for smuggling. Same thing at the border or in harbors. There are some control regarding smuggling, and If you put the control at the same place, again, it doesn't work. So here you have, again, you have two levels. You have the first level, who is going to decide what to defend, what to secure, which targets. And in the second level, you have the bad guys who decide what to attack or which animal to hunt, or and so on. And what is important in these examples is that you cannot repeat your strategy, the same strategy every day, as I explained. Otherwise, everybody, the bad people are going to simply evade in a simple way. And so the idea here in this kind of game is to use what is usually called mixed strategy. So the leader has a certain set of strategies. For instance, it can be here for the security, you have a different type of targets that you can decide to secure. Imagine you have 50 potential targets, but you can secure only 20 of them. Well, for every subset of 20 targets, this is what we call a pure strategy. And the mixed strategy is to determine a probability distribution on all those possible pure strategy. So you may decide to secure this group of targets with a probability 1/3, these are the group of targets with probability 1/4, and so on and so forth. And then, so these are the decision of the leader to determine the probabilities. And then on a given day, every day, there is a dispatcher, I would say, that draws at random the set of targets that will be secure. So the pure strategy that will be implemented on that day. And this decision is done according to the probability distribution. And then the bad guys, even if they observe this, they can observe this, the process during a certain time, and being able to determine what are the probabilities. But on a given day, they have no clue on which strategy will be implemented. And this is the win. This is the idea that is important behind this thing, and this is why it works. So, in fact, as I said at the beginning, this is related to what is called Stackelberg's bi-matrix game. And here I give you a very simple example of a 2x2. So you have here a leader and a follower. And you see the leader has two possible strategy, A or B. The follower has two possible strategy, C or D, okay? And here you have a couple, each entry is a couple in which the first coordinate represents the payoff of the leader if he chooses strategy A and the follower chooses strategy C. And 1 is the payoff of the follower. So first coordinate is the payoff of the leader, second coordinate is the payoff of the follower, okay? Now, if you look at this and you imagine that the two guys play with pure strategy, that means that the leader will decide which strategy is going to play, and then the follower observes this, knows this, and decides which strategy is playing, and the game is over. Okay, and now first let's play it in pure strategy. So decide exactly what it does. Then the leader, if the leader chooses strategy A, the follower has an interest, will play strategy C, because then he gets a payoff of 1 instead of 0. Okay, so if the leader plays A, the follower plays C. Now, if A plays B, if the leader plays B, then the follower will play D, because he gets 2 instead of 0. Okay, so this is the Stackelberg solution in pure strategy, because the leader gets 3 and the follower gets 2, and if the leader would have played A instead, he would have obtained 2, which is smaller than 3. Okay, so this is the Stackelberg solution in pure strategy. But now imagine that there is that the leader, that the game is played every day, and so the leader decides to play mixed strategies. Okay, and the idea would be, well, he can decide every day to play either A or B with probability 0.5 each. Okay, if he does that, then the expected payoff of the leader would be 3.5, which is the average between 3 and 4. And if the follower plays D, he would get 1, which is the average between 0 and 2. So he would get 3.5 and the follower would get 1. Whoops, sorry. So first thing, you see that this is more interesting. If you play the game every day, you have better to change, to draw at random your decision with probability 1/2 here. These are this is the optimal solution in mixed strategy, because in expectation, you get a better payoff. Okay. And as I said, also, the advantage is that in this case also, the follower does not know what you're going to play every day. He knows the probability, but he does not know what you're going to do. So it's much better. So this is to show you the difference between mixed and pure strategy, and to show you that this is an advantage in this kind of game for security. Now, just one thing. Here, maybe I just want to mention, because we talk, very often people talk about Stackelberg equilibrium. And you may wonder what is it with respect to something that is very famous as Nash equilibrium. And I guess Didier will talk about Nash equilibrium on Wednesday. So I don't want to go much longer about this, but the difference is that if you have a Nash equilibrium, you're looking for a solution which is stable for both players, in the sense that there is no hierarchical relation between them. In Stackelberg, you have the leader that plays, then the follower. But in Nash, you have those two guys, and the solution is a Nash equilibrium if none of them has an interest in choosing another strategy when the other player has chosen the equilibrium. It's a stable notion, okay? And this is different. It has different interpretation. I guess Didier will talk about bilevel problem with Nash equilibrium inside. Well, I don't want to go further because I don't know exactly what he's going to talk about. I hope he won't be mad at me if I say that. Just what I want to say here, for instance, is that here, if you look in pure strategy, a Nash equilibrium may not exist. It's not the case in mixed strategy, but in pure strategy, for a simple bimetrics game like this, a Nash equilibrium may not exist, but there is always a Stackelberg solution. So just a different notion also. Okay, so to finish about the Stackelberg game, so also what is important is that, excuse me, to notice is that usually you have one leader who is deciding about which targets to secure or which control to implement. And then you have several followers of different types, let's say. You can interpret this by saying that you don't know the precisely the utility of the follower, and so you define different types of follower with different utility, and then you associate a certain probability to each type, or there may be several type of followers and only one is going to appear in the game. Okay, and as I showed you in the small example with 2x2 matrix, you have a matrix of reward for the leader that is denoted by C, and here, and each type of follower has also a matrix of payoffs of rewards. And so you obtain a following bilevel formulation for this type of game, which is the following. You have two groups of variables. Here, two groups of decision. You have the decision of the leader, and then you have the decision of the follower. The followers, there are several followers here. For the leader, here I assume that I have limited, I know precisely what are all the pure strategies of the leader, and xi represents the probability of corresponding to the pure strategy I. So you see here in the first level, those constraints specify that xi represent a probability distribution over all possible pure strategies. Each probability must be between 0 and 1, and the sum must be equal to 1. Okay? Now, the objective of the leader is here. I will detail it. So I have a set capital K of followers. Pk represents the probability that this type of follower appear. And here I have Rikj, which is the payoff of the leader if follower K appears, and if this follower chooses strategy J, and the leader, chooses strategy I, so Rkij is the payoff of the leader if he plays strategy J, and if player K, the follower K, plays strategy J. Okay? And here you have the product of two variables. One is xi, which is the probability that the leader plays strategy I. And qjk is a 0-1 variable, in fact, that is the decision of the follower. The follower K will decide, for instance, to attack target J, then Kj is equal to 1. So what you have here is the expected profit for the leader. You see, you need to sum over all potential followers, and for each follower, you have the reward that the leader can obtain, which is this reward Rkij, multiplied by those variables which determines whether these are the strategy that are chosen by the leader and the follower. And the follower is taking his decision in order to maximize his own revenue. So you see the follower has a different matrix here, which makes sense if you think about, for instance, the poacher, the smuggler, or the terrorist. These guys, what they want to is to attack, is to win. And here the reward is, on the contrary, if you catch the guy because you have secured the target that was supposed to be attacked. Okay? And so again, in the follower problem, the decision, now in the follower problem, the probability xi of associated to the pure strategy I of the leader is given, and is deciding, is choosing the strategy J. Mr. K is going to choose the strategy J that maximizes its revenue or its payoff, its profit here, its utility. You see? So here you, in fact, you could say, okay, RKJ must be 0 or 1. This guy is going to decide to attack one thing. But you don't need to impose this here because the constraints are so simple. You just have the sum of the RJK is equal to 1. It is maximizing something that is linear once Xi is equal to 1, which means that is just simply choosing the strategy J. Mr. K is going to play strategy J, for which this sum here, sum over I of theCijk xi, is the largest. He's attacking the one that is the most interesting, the most rewarding for him. But of course, the objectives are different. This is why the problem is bilevel. And the problem again is strongly NP-hard. So this is an example, another example of optimization problem. And there are many, as I told you before, there are many applications for this, this type of models. And the team that I mentioned here of Milin Tamber is not at, he was at the University of Southern California, but he moved now to Princeton, if I'm right, yes. And he has a huge group, research group, and startup companies working on all those applications. Very interesting. Okay, here we are. So this was the different examples I wanted to show you. Yes, just maybe before finishing here again, here we have, as for the pricing problem, a problem that is bilinear in both objectives, but the rest is linear. And again, once the first level variable are fixed, the xi, once they are decided, the problem here, the second level is linear. It's even more trivial than linear because this guy is simply choosing one option out of the different options he has that are available to him. So it's a very simple second bilevel problem that, and this is an issue, a thing that can be very well exploited in order to solve this kind of problem. Okay, I think I wanted to say something else about this, but now I forgot. Okay. Now I will thus switch to, I would like to talk about some modeling issues. I would like to show you some geometrical example to get you, to give you some intuition about the bizarre aspects of bilevel optimization and what's happening here behind there. So the first thing, you remember the first example I show you in production planning, that was a linear bilevel optimization problem. And so I would say these are maybe the simplest ones in the sense that it's linear, but it's not because it's linear that they are simple. In fact, as I will explain you a bit later, again, these problems are strongly NP-hard. So here is just a first formulation, general formulation of a bilevel linear optimization problem. So you see, you have in the first level, let's say that the decision variable, the real decision variable of the first level is the X vector. And then, so you have here an objective that involves both first and second level variables. You have some linear constraints. Same for the second level. You have some linear constraints here. And here, the objective involves only the vector y, because if I would have a term here involving the vector x and a linear term, given that the second level has no influence on X, this is meaningless. You can take it out of the optimization problem. Huh? This is once the X variable are determined, this has no influence on the objective of the second level. Okay. What I would like to do now first is to show you an example. So I take here a very simple one, the simplest example, a geometrical example to help you understanding a little bit what's going on. So I have here a linear bilevel optimization problem. I assume that the constraint here, xy2, this set xy2 is given by this polyhedron here in the space xy. I assume also for simplicity that I have two variables, so I can represent the story in the plane. X is the decision variable of the first level. Y is the decision variable of the second level. I have no constraints, additional constraints in the first level to start with. I only have here linear constraints that tells me that X and Y must belong to this polyhedron here. Okay? And now assume for simplicity that this function of the second level increases in this direction, in fact, amounts to maximize Y. Okay, doesn't matter. And the objective of the first level increases in this direction. Okay? Now, that means that first I want to introduce the notion of what we call the inducible region. The inducible region is the region of feasible solutions, X and Y, such that Y is the optimal solution to the second level for the given X. So for instance, here you see the feasible region is this. So X, the decision of the first level, must be within this interval here. And each time when I choose a given X, the second level reacts by choosing the Y that max such that G function G is as large as possible. So this red part here is what we call the inducible region, because for every given X, the best Y is on this union of two segments. Okay? And in fact, somehow you can see this inducible region as the region of feasible solution, because Y is the best response with respect to the X. This is the XY such that Y is the best response to X. Okay. And now the leader, so this is somehow the feasible region, and the leader wants to determine now the X such that XY belongs to this inducible region, and the function f is as large as possible. Okay. So I need to find the point on this red region for which f is as large as possible, which means that this is my optimal solution. Okay? So the first thing I would like to stress out here is that in this problem, you see that this inducible region is not convex. It's the union of two segments, but this is not a convex region. I mean, you take any point here is a convex combination of 2 points of the red region, but it's not in it. Okay, so this is one of the difficulty. Of course, this can allow immediately to spot this difficulty. Okay, here also we have a linear bilevel problem, And it means that we have some more properties, as I will detail a little bit further. And first thing, I want to take a second example to illustrate an important aspect, which are the coupling constraints. The coupling constraints, what is it? Well, a coupling constraint is a constraint that involve the first and second level variable, some first and second level variables, but it's a constraint that appears in the first level, not in the second. Okay, so here I say, you see in this formulation here, I have a first group of constraints saying, okay, X, which are basically the decision variable of the first level, they must belong to some set. Okay. But in addition, I say also in the first level that the couple XY must satisfy some additional constraints. And these constraints are in the first level, which means that the follower, the second level, is not aware of those constraints. Okay, so when this guy is solving his own optimization problem, he's not going to take those constraints into consideration. And here a geometrical illustration of this aspect. So I take again the same example as in the previous slide, but now you see I have this region X, Y2 and the region X. So assume this is the feasible region, sorry, this is the whole X intersection of X and XY2. XY2 is the feasible region of the second level. And I may have some constraint on the X variables, but anyway, given that the second level does not control those X variable, it's okay. So you have, this is the feasible region, let's say in X and Y for the second level. But I have here this coupling constraint, and here what these coupling constraints say, well, in fact, Y must be smaller than or equal to this value here. Okay, I must be below that. So now what's happening is the following. Once the leader chooses a value for X, the follower solves his optimization problem and maximize J here. So the inducible region is no different, because at the very beginning, okay, when X is here is small, well, the inducible region is this red segment. But from this point on until this one here for X between those two values, when X is here, for instance, the optimal response for the second level is a value here that is outside the feasible region, because it doesn't it violates the constraint XY1. So that means that this solution X here is not feasible, because there is no Y, no optimal Y that is feasible for this one. Okay? So that means that those solutions here are not feasible, are not considered, because they are simply not, there is, for those X, there's simply no feasible Y in the inducible region. And so now the inducible region is made of those two segments. And okay, it's not convex, but now it's not connected anymore. You see, you have two different segments, and this is what makes the problem more difficult. This is an additional difficulty. Okay? And so this is a very important aspect, I think, is that from a modeling point of view, when you the decision you make when where you put those coupling constraints. So if you put that coupling constraint in the first level, it means that the second level is not going to see them, is not aware of them. And if the optimal solution of the second level violates them, then the corresponding X is not feasible. They are simply eliminated. Okay? So it makes the situation very different from a modeling point of view. I will give you an example a bit further. But before that, what I would like also to mention is that I want to introduce the notion of high point relaxation. So now imagine if I forget the objective of the second level, if I consider a single level optimization problem in which I optimize the first level objective function under all the constraints of the first and the second level, then this is what we call the high point relaxation. Because it's a relaxation of our problem, of course. If you solve this high point relaxation, so if you maximize f1x plus f2x on this set, you're going to find a solution that is a relaxation, that is maybe not feasible for the optimal problem. We will see in just next slide an example. So it means that it's going to give us an upper bound on the optimal value of the problem. Now, it's a relaxation because, for instance, you remember the first example I showed you, the inducible region was here. So this is the high point relaxation now because I only have those constraints. Now, if you let me see. Yes. Now, if you look at this, the high point relaxation, if you want to minimize f in this set, so this is the high point relaxation. The optimal solution, the optimal value would be 0 because this is it's always f is as big as possible going down, so this is the best solution here. And you see the optimal solution here as a positive value. So this is this shows you that what may happen is that when you do this, simply the solution that you obtain, the solution xy, is such that y is maybe not the best response, which would be the case here in the high point relaxation. Okay, I hope this is clear now. And but this is an important concept, as we will see later, because it gives us a way for when we will see there's a way for, well, an approach to solve the linear bilevel optimization using some branch and bound approach. And this high point relaxation gives, well, if assume that you have minimization problem, for instance, this would give you a lower bound. Okay. Now, maybe also we are reaching more or less the end of this first talk, but I would like maybe to say a little bit still about modeling, because I think again about those coupling constraints and aspects. So I'm going here to talk about an example that I'm pretty sure Ivana tomorrow is going to talk about in much more detail, which are interdiction problem. I don't think she will talk about the shortest path interdiction problem, but and I don't want to go deeply into interdiction problem because this is her domain. But I think it's a nice illustration regarding modeling issue and to understand exactly what the bilevel problem is when depending on the way you model it. So here I consider what is called the shortest path interdiction problem. So I have a leader and a follower, and so you are given a graph, and you see there are weights associated to each arc of the graph, and the leader wants to interdict a set of arcs, at most k arcs, and his goal is to maximize the length of a shortest path from S, the source, to the sink, let's say here. So he wants to maximize the length of this path, because once the arcs are interdicted, of course, they cannot be used by the follower is going to travel from S to E. So, for instance, imagine that I interdict, well, the shortest path when no arc is interdicted on this graph, if I see well, is, I think this path, SCDE, okay? Now imagine that I interdict this arc, then of course the path is not feasible anymore. And in this case, you would go in this way and so on. So the problem is thus you want to, the leader wants to interdict at most k arcs, and the follower then reacts by choosing a shortest path in the remaining graph. Okay, the leader wants to maximize the value of this shortest path, and of course the follower minimize this value. So here we are going to have two types of variable. You have the variable xij, which take value 1 if the arc ij is interdicted and 0 otherwise. And then, so these are the, here, by the way, this is a pure strategy game. Here we do not, well, you can look at the version in mixed strategy, but this is a different story. So here, xij is equal to 1 if the arc is interdicted and 0 otherwise. And of course, the sum over all ij of the xij must be smaller than or equal to k, which means that the leader can interdict at most k arcs. Now, yij are the variable controlled by the follower, and they represent the path that is used by the follower. So yij is equal to 1 if arc ij belongs to the path that is chosen by the follower. That means that it must be a shortest path. Okay. So also here I wrote here below ny is equal to delta. This is just to mention. This means that this is a matrix way to write the fact that the y variable represents a path. So n is the incidence matrix of the graph. So the product of this matrix times vector y must be equal to delta, which is a vector in which the entry corresponding to node S is equal to +1. For node E, it is equal to -1. And for the other nodes, it is equal to 0, which means that if there is an arc entering, there must be an arc leaving. So this is just to model the path aspect. Okay, so I assume you are familiar with this. And now, in fact, you can formulate the problem in two different ways. And Ivana is going to talk about that much longer. But I would like to stress, to show you that the way you model the problem may have different consequences. Let's see. First, the first formulation here on the left uses the following observation. In fact, if an arc is interdict, it is as if it would have a very high cost, so high that the follower is not going to use that arc. Okay, so that means that here you have a model in which the objectives are bilinear, and you see the objectives gives you the cost of the path, but for each arc, well, this is written in vector form. So this is, oh, sorry. This is the product of vector y and c plus mx. So for each arc, you have a cost Cij plus m times xij. If xij is equal to 1, so the arc is interdicted, that means that the cost of this arc becomes very high. It is Cij plus m. On the contrary, if the arc is not interdicted, xij is equal to 0, and then the cost of the arc is Cij. So you look for a path for which has a minimum cost with respect to those modified costs, Cij plus m xij. Okay? Here I simply, E is the vector with all one, so this amounts to say that the sum of the xij is smaller than or equal to k. The xij are 0, 1 variable. Each r can be interdicted or not. And in the second level, one requests that the follower is choosing the path which minimizes the value, okay, with minimum cost. Okay, so this is one way to model the problem. Fine. Another alternate way would be to say, okay, in fact, instead of having the information regarding the interdiction of the arcs in the objective, I will put this in the constraints of the follower. So now the cost of the path is given by the sum of the Cij, Yij, so the cost of the arcs that are in the path, but I forbid the path to use the arcs that are interdicted. Here, in the constraint of the second level, I have for each arc a constraint saying that xij plus yij must be smaller than or equal to 1. If the arc is interdicted, so if xij is equal to 1, then yij must be equal to 0, which means that the arc cannot be in the path. Okay? And here I have the flow conservation constraints, or simply the constraint that says that y must determine a path. I assume, of course, here that all arc have a cost that is non-negative. Yeah, because I want to avoid issues regarding cycles. Huh? Okay, now those two models are equivalent. In fact, Ivana will explain you that I have modifying the objective function amounts to remove those constraints and penalize them in some way, in a different, well, to represent them in a specific way in the objective. But okay, those two models, they are equivalent provided that the number of arcs you can interdict is smaller than or equal to the number of arcs in a minimum cut. Indeed, here, if you look at this graph, imagine that I can interdict 3 arcs. Okay? If I can interdict 3 arcs, I can interdict those 2 and another one, let's say. Oh. But then, if I interdict those 2 arcs, there is no path anymore between the source and the sink. Which means that there is no feasible solution here. If I interdict the 2 arcs going out of the source, the second level here is not feasible anymore. Okay? Which means that now, in this case, the two models in this situation will give you different things. They do not mean the same thing. They are not equivalent anymore. So if I can interdict too many arcs, so in such a way that there is no feasible solution anymore. So in fact, if K is bigger than the connectivity number of the graph, which is the value of the min cut. Here, with the left model, if you solve it, in this case, what you're going to obtain, you always have a feasible solution here, whatever the decision you take in the first level, X, because all the arcs that are interdicted get a very high cost, but you can still use them. The second level can still use them. So in this case, this model is going to give you a path somehow that uses the least number of interdicted arcs. And here it's different, because every path, every interdiction plan such that the second level is not feasible is not an interdiction plan that is feasible for the leader, because there is no solution. So this model here, if you treat it in this way, what it is going to give you is an interdiction plan such that there is a feasible path, but for which the cost is as big as possible. So here, all interdiction plans that disconnect the graph are considered as non-feasible. And here, they are considered as feasible, okay? So you really have to pay attention to this kind of thing to know very well what you want, what is the reality, and to model it in the appropriate way. I think this is very important. Of course, you say, well, this is easy. I can easily check whether whether K is too big or not, and then I can decide which model I'm going to use. Okay, but this is a simple case. In general, it's not always as easy to see whether for every decision of the first level, you have a feasible decision of the second level, and what are the consequences for your problem. And this is what is important, I think. Well, this was what I wanted to say so far. And I think now I have reached the first lecture, the end of the first lecture. If I right, I'm even 2 minutes too late, so I hope you won't mind. And I propose to have a break now.